join the Jam with long-term thinking. And welcome, Dr. Gavin Wood.
Thank you. So here we are for number 8 of the Jam Tour 2025. Thank you all for coming. It's a bit of a long talk, so, sorry. I won't be offended if you need to go out for a glass of water or something. Good. I'm thankful to Obi for putting this talk into some context. I think it is important to understand the historical context of why we're doing this, where we're coming from. And I'm going to continue on that direction and contextualize things a bit further, narrowing down to our present time. So our industry, the sort of blockchain Web3 industry, is increasingly dividing. And we see on the one side the longer term thinking, the teams that are really trying to solve the hard problems with this technology. And on the other side, we see the teams that are really out there to, I think if I were to be cynical, I would say to milk the market. But certainly who are much more focused on short-term results. Now, I actually gave this very same slide in the early Jam talks 2 or 3 weeks ago, before the Bybit hack. And it is unchanged, apart from the extra bold at the bottom there for blind signing. I was telling people they should not be blind signing for short-term results, and Bybit really gave me a very helpful example of why we should be not blind signing. There are various other things on that list, and I think it's fair to say that most blockchains and most blockchain teams don't pay them very much attention. We often see some very large and increasingly backed by certain quite powerful individuals blockchain networks with very small validator sets, highly centralized, high power nodes required to run them. We see bridges still with N of M multisigs just waiting to be hacked. We see a huge amount of focus on speculative tokens. We see increasing pandering to incumbent elements, disregarding what the technology is there to do. The teams that are really trying to solve the hard problems are trying to do things like scale whilst retaining decentralization, not merely making their nodes go faster. Trying to build light clients in order to avoid RPC hacks. Trying to build actually trustless bridges in order to avoid governance hacks or N of M multisig hacks. Trying to actually imbue maintainable, sustainable economics into their tokens, or remove the tokens altogether if they're simply not required. Trying to bundle rich metadata in a trustless way with their transactions to be read on some secure cold signing device, rather than just assuming it's fine and blind signing. These 4 things are not the same. They're related. They're certainly terms used in this industry, but they're not the same term. They don't have the same meaning. Now, cryptocurrency could be described as maybe a resource, or at least a vertical within the broad Web3 industry, blockchain industry. Blockchain is a technology, and I'm going to try to explain to you precisely what this technology is in a second. And in this industry, DeFi is another vertical. It is not the only vertical, and it certainly doesn't encompass all of Web3. It is a small corner of Web3. Web3 as a whole is an approach. It's a technological approach, and a new technological approach. Not one that has been, to my knowledge at least, pursued in the past. So what is Web3? Well, there's a few ways of explaining what Web3 is. But Web3, if you like, could be described as building or an approach to building resilient public digital infrastructure. Now, the main difference between technologies or approaches that have gone before Web3 and Web3 is that of resilience. Web3 is resilient. Indeed, some Web3 systems could reasonably be described as being anti-fragile, which is to say benefiting to some extent from chaos and diversity. Resilience here means resilience against a lot of different things. We're not building Web3 to be particularly strong against one particular sort of malevolent force around it. Web3 systems are designed to be resilient against a number of, well, essentially every different possible force that might attempt to corrupt its output, including some very important ones, such as the owner or the deployer of the system. I mean, Web3 systems don't have owners generally, but they generally have some sort of creator, a team that creates it, or individuals that deploy it. Now, most of the time when we think about digital systems, we don't think that it needs to be resilient against the very entity which created it or deployed it. But in Web3, we do, because Web3 systems are public systems in a very broad sense of the word. We must also make them resilient against situations that we don't expect to happen. The unknown unknowns. So in some sense, Web3 really is a revolution in how we interact with the world, in the same way that the internet was also a revolution in how we interact with the world. It is, if we're trying to think very broadly, Web3 is a way of trying to create that resilient infrastructure, public infrastructure, but within the internet. Now, there's a few elements to Web3, and I wrote this down like 10 years ago in a blog post. Broadly speaking, the services of Web3 could be split into three parts. One of them is publication of static data. One is messaging, so transient data, communication. And the third is consensus, economic signaling. And my proposition is that if we have these three things, and if they're all resilient, then we can deploy any Web 2 app in this new model. They need to be re-architected in order to utilize these services, but in principle, they should be possible to deploy, to essentially move into this new platform. But probably the most important of these resources is the third one, this sort of consensus computation. And it's called, we can call it block space. I mean, other people call it block space. It's a bit silly. Historically, it refers to space inside of like a Bitcoin blockchain, which is a bit silly because Bitcoin's block space is particularly inflexible. But it is what it is, so we use this term. Now, the different block spaces that are produced by all the various different blockchains vary quite substantially in a number of different properties that we can measure. Block space is not all the same. Some of it is much more valuable than others. So blockchain is actually just a decentralized computer. Yeah. What does it mean to be a decentralized computer? This is a bit of a strange term because computers are not decentralized. Here is a computer. You can see it. It's obviously not decentralized. I'm holding it in my hand. It's very centralized around its physical form. Anyone with access to its physical form has essentially total control over it. I could take a hammer and smash the computer and then it would stop working regardless of who was trying to use it. So what do we mean by a decentralized computer? How do we decentralize a computer? Well, I mean, I think pretty obviously one cannot decentralize a physical computer, right? The fact that it is physical implies that it is centralized. But when we say a decentralized computer in this sense, what we mean is a model of a computer. We model a computer for its essential parts, the computation elements, essentially. And with this model, we decentralize. So we manifest the model through the amalgamation or the emergent effect of many different physical instances. And this is what we mean by a decentralized computer. And the main point of it being decentralized is that we can remove or corrupt some of these physical manifestations, some of these physical instances, some of these nodes that are helping us create this virtual decentralized computer, and it won't affect the correctness, the manifestation of this model. It doesn't need all of them to be correct, it just needs a few. Generally, it means it needs 2/3. Now, over time, if we look at history, we find that there tends to be 3 stages in new technologies. The first stage is when the technology is initially introduced, and it's very focused on solving a particular problem. Generally, the problem had a sufficiently great economic benefit that it was worth the cost of developing the new technology. Right? So the technology is developed to solve a particular pressing, important, valuable problem. And so initially, when we innovate, technology tends to be very, very focused around one particular domain or one particular problem set or one particular use case. Generally, over time, people in adjacent domains, in other contexts, in other industries, in other situations, realize that this innovation can help them solve their problems. And so the innovation sort of mutates into other domains. And not long after, generally, someone comes along and realizes that this innovation, the key elements of it, are actually useful in many different domains, and they generalize, they abstract, and they create a piece of technology which is applicable to solving the problems in all of the domains equally. A generalization. Now we see this with computers. The first computers were very domain-specific computers. They were created oftentimes to solve one particular mathematical equation, one particular formula. And then over time, other computers were created for other formula, and eventually someone realizes, actually, maybe we can make it programmable, so we can alter which formula the computers do. This became the first programmable computer, really just a calculator, because the operations were so very particular. Eventually, someone realizes that the set of problems that computers are applicable for go beyond solving very specific mathematical equations and can be used for things like business. We see programmable mainframes. We see academia starting to bring in computers. And over time, it generalizes until eventually we end up with we end up landing on certain instruction sets, like ARM64 or x86, x64, where we are able to not only have a general problem-solving machine, but we have a standardized a standardized machine for problem-solving. And this allows us to commoditize. And this is where we get to the third stage. Now, with computers, this is basically PC compatibles, and then later cloud revolution, right? Essentially the ability to buy standardized resource regardless of the vendor. And then the market competes on smaller deviations from this standard, added extras, or cost, price. Now we see the same with blockchains. Early blockchains are very domain specific, Bitcoin being the obvious one, but there were others, Namecoin to name a second. There was some generalization, like with Ethereum. And there's more generalization since, like with Polkadot, which utilized WebAssembly and was able to not only do smart contracts, but also do various other things like validating other blockchains. And we're going through further generalization now. And it won't be too long, in my opinion, before we get to the point of commoditization and the ability to buy some general block space, regardless of who is vending. And Polkadot is designed to create the highest quality block space. So how do we measure quality of block space? Well, there's a few different ways. Block space is, at the end of the day, time on a decentralized computer. So one of the ways that we can measure it is by how much computation can that decentralized computer do in any given period of time. Polkadot is through its essentially ability to scale out problems across the nodes on its network, rather than just give the problems to every node and have them all recomputed. Polkadot's able to scale substantially and therefore provide a lot more computational throughput. Now, transactions per second is a very ineffective and vague way of measuring computational throughput. But nonetheless, it seems to be one that is quite resonant within the industry, and so we play to that particular tune. As you can see, Polkadot's fastest recorded transactions per second on a live network is substantially higher from all other blockchains. It also happens to have the highest bandwidth. Another way of measuring block space is by how much data can it bring in, how much data is it able to work with, and how much data is it able to store. Now you can measure this by what's called the availability bandwidth, or the amount of data that its availability system is able to process. And as you can see, Polkadot's availability system is actually substantially better, not only than regular blockchains like Ethereum, but also than domain-specific blockchains whose main or only purpose is to provide data bandwidth. One way of measuring resilience is through the decentralization of its node network. Specifically, how many different economically independent nodes would be required, or economically independent actors, I should say, would be required to collude or to be compromised before the network itself would break. We call this the Nakamoto coefficient, after Satoshi Nakamoto, the pseudonym of the Bitcoin author. As you can see, Polkadot's Nakamoto coefficient is substantially higher than any of the other major blockchains, giving it far more resilience against potentially compromised nodes or colluding validators. Now, Polkadot also happens to be the most energy efficient. Energy efficiency is also can be used as a proxy for another measure, which is cost of computation. And this is an underlying threshold for how cheap it is possible to run transactions. As the transaction volume goes up, the cost will eventually, per transaction, approach something that is proportional to this. In principle, that means, therefore, that Polkadot can provide transactions quite a lot cheaper, like 20 times cheaper, than some other, than all other ecosystems, and a lot cheaper than some other ecosystems. The way that it's able to do this is by scaling out rather than scaling its nodes up. And this is gonna be a pretty, I hope this will resonate, and I'm gonna keep returning to this theme over the course of this lecture. Another way that, so Polkadot is able to do this, as I say, through parallelization, distributing its workload across many nodes rather than having every node do everything. We call this essentially sharding. Polkadot benefits from shared security. Now, this should really go without saying, but unfortunately, some networks, notably Cosmos, are trying to suggest that having multiple chains without shared security is somehow comparable to a shared security situation. Crucially, shared security allows us to have economic scaling, or for multiple different ecosystems, the economies of multiple different ecosystems, to come together and each take a portion of the burden of security for all of them. And this gives you economies of scale. Polkadot also has really pushed the concept of cross-chain interoperability with its XCM format, cross-consensus messaging format. And this allows different chains that are domain-specific to advertise and accept services within a common language. And as I mentioned, Polkadot's data availability, outperforming other chains' data availability, even ones that are made specifically for data availability, is provided to those on Polkadot at no additional cost. Now, I mentioned that Polkadot, beyond Ethereum, is trying to build a Web3 cloud. How do you build a Web3 cloud? This is a bit of an odd concept. A Web3 cloud is like a resilient Web 2 cloud. And how do we think of Web 2 clouds? How do these begin? They begin with a computer. Generally, they begin with a very fast computer, and then more computers are added as the cloud needs to serve more customers. So, how do we build a Web 3 cloud? Well, we need to begin with a Web 3 supercomputer, a very powerful Web 3 computer. And then we need to be able to add more Web 3 computers as the amount of demand exceeds the supply. So this means that these computers in principle have to be able to be connected and composed with each other. I'm not going to get too much into that, but I will discuss Jam, which is the basis of the protocol by which we deliver the Web 3 supercomputer. The rest of the talk will be focused on Jam. But this should have given some context as to why we're bothering to develop Jam. Jam is necessary in order to create the Web 3 cloud. So, Jam is not merely another blockchain network. Indeed, Jam isn't really a blockchain network at all. It's a protocol. The blockchain network it's expected to be deployed as is Polkadot. Right? So Jam is really a protocol definition. It's purely a technology. And this protocol, it's not a piece of code. It's a specification. And it's written out in a document called the Grey Paper. Jam is what I call protocol first, not software first. You will see other blockchains that are totally based around their software implementation. Generally just one, sometimes two, right? Very, very few networks have more than two implementations. Very few of them provide a formal specification of their protocol. Ethereum was the first, and actually it was me who did it with the yellow paper in 2014. For those of you who are familiar with the yellow paper, there is the grey paper, which, being Jam's formal definition, actually, as you might expect, takes some of the elements of the yellow paper Like the format, some of the notation is quite reminiscent of the yellow paper. The structure also. If you can read the yellow paper, you can probably have a good go at reading the grey paper. By making it protocol first, we avoid the possibility, or at least we really reduce the probability of a specific development team becoming the only viable development team, or a specific implementation of the protocol becoming the only viable implementation of the protocol. If there is really just one implementation of a protocol, or if the vast majority of nodes on a network only use one implementation of a protocol, that is centralization again. It was for this very reason that we created the yellow paper. Ethereum was protocol first, not software first. It was to avoid a single implementation being the dominant one across the network. And this is something that with Jam, we really, really want to avoid. And so with Jam, the grey paper will be published before any particular implementation in order to give lots of development teams a chance of implementing it before any sort of consolidation over a particular implementation happens. In order to try to incentivize teams to implement this protocol, there's a fairly substantial prize pool, 10 million DOT. And this is available for teams who can demonstrate that they have implemented the Jam protocol correctly. In addition to this fairly substantial sort of financial incentivization, there are some other pieces of support that teams get if they implement Jam. On-chain salaries as part of the Polkadot fellowship system. Invitations to international seminars, professional security audits on their code base, and hardware access so that they can test out their node on real final validator hardware, which is not maybe everyone particularly wants to invest in. They also get access to a machine called the Jam Toaster. I'll get to that in a second. 36 independent teams have come forward and said that they are implementing this grey paper. They are implementing Jam. And they're using, I think, about 15 or 16 different programming languages. I mean, they're not each using 15 or 16. But, each of them is using one of 15 or 16 different programming languages. Diversity over programming languages is also important. There are many areas of centralization that can be really problematic for a blockchain network like this. And it's important that we try to avoid this kind of single point of failure. So the Jam Toaster. The Jam Toaster is a small supercomputer. It's not really a supercomputer that's comparable to any of the modern big supercomputers. But it's also not just a regular server either. It sort of sits in the middle. It has about 16,500 AMD Threadripper 5 GHz cores. 32 terabytes of 8-channel RAM and 16 gigabytes of L2 cache for those processors, as well as some pretty heavy-duty networking and storage. Why are we building this small supercomputer? Well, this is a very important element of Jam. Simple blockchain systems like Ethereum do not particularly rely on the emergent effects of the nodes. If I run a single node Ethereum network, it will do much the same thing as if I run a 10,000 node Ethereum network, which is to say it will go through and process the transactions in a block. Yeah. And it will author blocks, allow new transactions to come in and update its state. Both will do this. It's just that one, the 10,000 node network, those nodes state are replicated 9,999 times. Whereas if it's just one node, it's not replicated at all. It's just that my node runs. When we build networks like Jam, it becomes a little harder. Because the network as a whole does not do simply what a single node does. Rather, the nodes work together doing different things, and what the outcome of the network is what we call emergent. We rely on the emergent effect of the nodes on the network. And this emergent effect is very different to the single effect of one node. It's a little bit like trying to imagine a market. Where does the price come from? Well, the price of, say, apples in a regular market comes from the emergent effect of, well, the people who have apples to sell and the people who want to buy apples. And they all sort of do their thing, and eventually there is a consensus on the price. No individual agent sets the price. Yeah? If we take one person from the market and say, what's the price of an apple? They will not be able to give the same answer. No. In fact, the answer comes as an emergent behavior of the system when it is full of agents. Well, it's the same with Jam. And this gives us a problem. When we have a single system that a single person authors, then the code, the instructions that the machine is working through are specifically designed to give the behavior that we want. There is a clear mapping between the software that is written and the behavior that we want. We do this with, say, unit tests. And we write unit tests that make sure that the software does the behavior that we want. And then we can have debuggers that allow us to go through the execution of the software and allow us to check when the software's behavior deviates from our expected, our desired effect, our desired behavior. Well, when we have an emergent system, we can't do that. Because every piece of software isn't on its own giving us the effect that we want. It's only with the system altogether that we get the effect that we want. We have effectively separated the workings of a node from the outcome of the system. The workings and the outcome are now separate. This makes it really hard to engineer well. Oftentimes, when you're counting on the emergent behavior, you'll find that your system goes suboptimally. It goes slow, it has bugs, it might stop. And it's very hard to understand why, if you can only look at one node at a time. It's very hard indeed, maybe even impossible. It's almost like you're trying to work out how a whole forest is mutating by only looking at a single tree. Now you might be able to see if that single tree is having trouble in its current environment, and maybe it's making way for some other tree or something. I don't know. But it's very hard to understand the dynamics of a forest simply by looking at a single tree. In the same way, it's very hard to understand how an emergent system is working or is failing on the basis of looking at just one or two nodes. The Jam toaster is designed to be a full-scale test network for Jam. So we can run the whole of Jam as a test network in this one machine at full performance, exactly the same performance profile as if we actually had 1,023 different validators all running properly spec'd nodes. And the main difference is that this is all contained in a single room, which allows us to hook it all up to a logging system and actually analyze and create network conditions so that we can really understand the emergent behavior of the jam network. And this is, to the best of my knowledge, the first time that this has been done for a blockchain. But it's absolutely necessary if we are to move blockchain beyond the distributed ledger concept. So, what is jam? There's a little picture of jam. It's a bit like a flower. There's a central bit, and then there are petals. In fact, there are several hundred petals, 341 petals, in the current expectation of a single jam machine, single jam instance. Around the petals, there is storage, decentralized storage, decentralized distributed data lake. And as you can see, data comes in from the outside through the petals and into the middle, where it can react with all of the other stuff coming from the other petals. This is the basic architecture of jam. But before we get too deep into that, let's look at what has come before and try to understand why this is a sensible design. So there are five that I have identified, 5 driving factors when engineering blockchains. The first is the most important, and it's resilience. This is something that Bitcoin, Satoshi Nakamoto, demonstrated was crucial. Bitcoin didn't really have, it had a couple of the other things maybe, but it didn't have generality and it didn't have performance, but it had resilience. Bitcoin is still going, right? It survived a lot. It's had to be resilient because it has survived so much. Now, as I mentioned before, that Bitcoin was sort of the first piece of technology, very domain specific. Generality, to some extent, came next. Ethereum provided a more general system. And then later, Polkadot increased performance of blockchain by several orders of magnitude. Coherency is another element that is very important, though, and not one that Polkadot provided. In fact, Polkadot gave a performance coherency trade-off. So if we try to sort of picture this, Ethereum 1, as we know, it's very unscalable. I've done a little picture there of it. Now you can try to just basically make the same thing bigger, right? Which is what some networks have tried to do. Take the same model and scale it up. Just make the nodes faster, right? EOS was a very good example of this. There are others. These are also unscalable. Right? They eventually hit a limit, which is how fast you can reasonably require a single node to be, minus the network synchronized, basically the state replication overhead. They also tend to be very fragile because they rely on very particular optimization techniques, generally only implementable by one team in one piece of software. Oftentimes, only one person or two know how the optimization techniques work, and this can create huge amounts of fragility. And the more that you increase the barriers to entry to running nodes, the more centralized you will end up making the network. I mean, that goes without saying. And so we end up disregarding some crucial elements of Web3 in order to trade off for some additional performance. Okay, so if we can't scale up, let's scale out. Let's make new networks. This is one thing that, for example, Cosmos has sort of been pushing to do. Our problem with actually just literally deploying other networks with other validator sets, with the capital pools, is that there's no great reason to believe any new network is actually secure or anywhere near as secure as the networks that have already got a decent amount of capital behind their validators. Now, that's one issue. The other issue is an issue actually that we've seen throughout scalable blockchain approaches, which is that there's persistent state partitioning. What do I mean by this? Essentially, as we add a different network, operating within that new network is harder than operating in the old network if we want to be interoperable with the other things in the old network. So suppose there's a DEX inside of a network, and that network gets congested. And so someone comes up with the idea, let's launch our own chain. Well, that's fine, and your own chain indeed won't suffer from that congestion because it's its own chain. It won't have any traffic initially. But if anyone in that old chain, or indeed a contract within that if a contract in your new chain wants to interact with the DEX, they have a problem because they're not next to the DEX anymore. They're not in the same network as the DEX. They in fact have to bridge over and send messages and then wait for a while. If they have a flash loan system in the new network, it will not be atomically composable with the DEX. It will not generally be usable. Now, in addition to this, creating new networks, it tends to be a harder thing than deploying a smart contract. And in the Cosmos model, where you have to actually create your own validator set as well, it's very high indeed. So let's look at Ethereum. Ethereum had this kind of very, this is a slightly older Ethereum roadmap. These slides were done, I think, a month ago. And Ethereum in the last month has U-turned again and has decided to switch out its L2 rollups roadmap for native rollups roadmap. But regardless, even if the native rollups versus L2 rollups reduce to some extent the patchiness of the overall scaling solution, if they're L2 rollups, we're going to see all sorts of different properties depending on the rollup. Potentially different latencies to finality, different versions of the EVM used, different security characteristics, different centralization factors, and so on and so forth. But even still, even if these things are fixed, we're still stuck with this persistent state partitioning. If you're in one rollup, you're not in another rollup. It's easy to interact within your rollup. It's hard to interact between rollups. Polkadot. Now with Polkadot, we have homogeneous security guarantees for each of our different rollups or parachains. But we still have this persistent state partitioning. If you're in one parachain, you're not in another parachain. Yeah. So why do we do persistent state partitioning? It's an odd thing to do if it's really hurting us so much. The answer is actually very simple. It's a fundamental antagonism between the scale of a system and how coherent it can remain. As systems scale up, then the individual elements of the system, the individual portions of the system's state, become farther apart. Yeah, the distances grow. The average distance grows. And interestingly, the variance of distances grows as well. As a system scales up, if we imagine a distribution of all of the distances between all of the items to all the other items, then that distribution would probably look something like a bell curve, but the mean would increase, and the bell curve's general values would get higher, but also the bell curve would start spreading out. Yeah? Some portions of state, some pieces of this machine would still be quite close to each other, but some pieces would be really far away from each other. And most things would be quite far away. Now, given that we know that cause and effect has a fundamental speed in physics, the speed of light, we can therefore understand that causality, if we want to make a system which is computational, which allows us to have cause and effect on a programmable basis, then as that system grows and handles more state, it either has to slow down to give the far away things a chance to resolve, a chance for the effects to resolve, or we have to partition it up so that there are no faraway things, and everything is just close to everything. And we can't do that if we have too much data, so we have to basically split it up, parcel it up into separate things. And this is actually where persistent partitioning comes from. We parcel up our big system, the whole of Polkadot, the whole of Ethereum and L2, into smaller systems, parachains, L2s, systems that can't affect each other directly, but they can at least communicate asynchronously with low bandwidth through messaging. And this is how we manage this size, coherence, antagonism. And this isn't something that's specific to blockchains at all. You will see this everywhere if you just look for it. You see it in biology, you can see it in chemistry, you can see it in CPU design, everywhere. It's just a fundamental part of the world. So, if we could have what we wanted, what would it be? How would we draw it? And here is my effort at drawing the ideal thing, the ideal situation. The bold border on the outside there is the fact that it's a shared state. It's a single state machine. And the arrows going from top to bottom indicate that this has a number of different actors or smart contracts that are operating in it. Processes, if we're talking about operating system level stuff. And the fact that I couldn't draw very many of them, I got bored after 9. But the fact that there's lots of arrows indicates that there can be lots and lots of these actors or processes or smart contracts. They're sharing this box so they can interact with each other atomically as they choose. This is what we'd like, right? This is what we'd like. What did we get? Well, with Ethereum 1, this more or less is what we got. So we've got our box, that's good. They're all sharing the same environment. But after that, it kind of breaks down a bit. Well, we've got a few arrows. That's nice. Now, if you notice, the arrows don't overlap, indicating that only one smart contract operates at a time. And there's a huge amount of space in between these arrows. That indicates that between the blocks, there's a lot of idleness. The Ethereum network doesn't actually do that much computation. It spends, an average Ethereum node spends upwards of, at least 95% of its time not doing anything, not really doing anything, not processing any transactions anyway. And most of the time, even more than that. 95% is quite a low estimation. This isn't ideal by a long shot. Now, the fact that I drew it in blue rather than orange indicates that the sort of memory and storage isn't so normal, right? We have very particular memory and storage in systems in Ethereum. Right? The storage is like this crazy 32-byte to 32-byte mapping thing. It doesn't look at all like a file or whatever. And similarly with the memory, right? It's all 32-byte stuff. It's not like a normal computer, and normal programming languages don't really understand this. Now, if only one of these arrows operates at once, then actually we can simplify this, because it doesn't matter if there's like multiple small state machines that operate only one at a time, because we can also just draw that as one bigger state machine that just operates continuously. Yeah. So it's just simpler for me to draw it in the right side. So as I say, there are some high performance synchronous networks, Solana, EOS, these sorts of things, that keep the basic Ethereum computational model with a few little changes, like potentially some multi-threading support, so that two things, if they're not operating on the same memory, can sort of squeeze in a bit more processing time by having them execute sort of at the same time, or parallelize at least on a CPU. So they can squeeze a bit more out of the hardware through optimizations. And so I've drawn the arrows a little bit thicker. But it's still basically only one at a time. If you're lucky, you might get 2 or 3 at a time. And there's a bit less idle time between the blocks. Yeah. So there's a bit less space between the 2 arrows there at the right side. But it's still the same model, still the same computational model. Yeah, we're still replicating everything across all nodes. We're not really using our big node network to do anything useful. I can look at Cosmos. How does Cosmos look in this graphical language? Well, we have basically what we had on the right side there. Maybe the arrows are a bit less thick because we don't have so many optimizations. But basically, we've got several of them. And they can kind of talk to each other. But when they talk to each other, they have to go outside of the consensus and back in again. The bridges are going to be only as strong as the weaker of the 2 entities that are talking over it. And overall, with the system taken as a whole, we are effectively dividing our security. So we're dividing our capital basis, the economic basis on which we attribute our security. And if we divide our capital amongst multiple networks, we're effectively lowering it. Yeah. What about Polkadot 1? Well, it's a bit more sophisticated. We've got our thick border on the outside there, and the arrows are all inside. That's good. That means we're doing something sensible. The arrows are in some sense sharing some state space. However, we have our bars going down, vertical lines going down from top to bottom, indicating that actually we've partitioned our state space up. Yeah? Now the arrows can't directly interact across that thick line. So instead of interacting across the thick line, they send messages. Oh, like Cosmos. Yes, like Cosmos. Except their messages stay within the thick border. Their messages are secure. Yeah? They don't have to go outside. They stay inside. So this is basically a reasonable graphical representation of what's going on in Polkadot, or the Polkadot sort of original Polkadot concept, parachains. And modulo a few things, this is probably more or less where Ethereum is headed with its native rollups. So what's Jam? Here is a graphical representation of how Jam works, what's going on inside of Jam. So we have the, on the left side there, we have our DA, as it would be called in sort of Ethereum terms. I'm calling it the data lake, or the decentralized distributed data lake. And this is a large scale data store for Jam. For Jam software to store its data and get it back again. On the right side is basically a blockchain, fully synchronous state, as we sort of already know. We can see these blue arrows. They're not overlapping. They actually can overlap in a future version of Jam, but at the moment, they're not overlapping. In the middle is where Jam gets interesting. The middle are what we call our coprocessor cores, or our cores for short. These are computational elements. They're independent of each other, but they can each read from the data lake, as you can see with the data lake having arrows going down, and they can each write, like submit data into the data lake, as you can see from the arrows going back across to the data lake. In addition to that, when they execute, they submit their result into the blockchain. So you can see the arrow starts in the data lake, goes through one of these big, fat computational coprocessors. And then at the end of it, forks out with some data going back into the data lake and other data going into the blockchain. This is JAM. This is the basic architecture. So JAM introduces a new computational model, which I'm calling transient decoherence. It's mostly coherent. So the system as a whole remains mostly coherent, mostly operating out of the same state space. But a small portion of its state, which is to say the most recent computation, may be incoherent, but it gets resolved with a finite time span, within 6 seconds, as it turns out. And this is an alternative answer to the problem of scaling a system and managing the fact that it has to somehow become incoherent. We have to somehow manage the problem of size, coherence, antagonism. This is an alternative solution for this. In some sense, it's actually quite similar to modern multi-core CPU designs. Some of the ideas present in JAM are directly identifiable as patterns in modern CPU design. So JAM has two computational environments, two execution environments. One of them we call in-core, or using these coprocessors. That's the computation done in those thick arrows in the middle, in-core. The computation done on the right side, the thin arrows of the blue background, that's on-chain. So we have these two models of computation. Now the in-core computation has access to that massive data lake, but it's stateless otherwise. Whereas the on-chain computation is stateful and it's synchronous, but it doesn't have the huge amounts of computation muscle, nor does it have access to the huge data lake. Now the data lake is 1.5 petabytes big. That's very big. And it has an intercore synchronization latency of 6 seconds, which basically means if something writes into the data lake from one of those thick arrows, it will not be visible to any other thick arrows until 6 seconds later. This is a little bit like if you're working on a CPU core and you write something into RAM, then none of the other cores will be able to see that until effectively your cache has been flushed. Yeah? It's kind of the same thing. If you happen to be wanting to read from it on the same core, then just like with CPU design, when you're reading from the same core's cache, it will be instantaneous. The distributed decentralized data lake, that massive rectangle on the left side, this stores segments of data. A segment of data is a fixed size of 4 kilobytes, actually just over 4 kilobytes, 4,104 bytes. It's 8 bytes in addition to the regular 4,096. And you get to look up into this data lake by using a cryptographic commitment. Yeah, a 36-byte cryptographic commitment. Now, if we rephrase this in Ethereum terms, which might be helpful if you're already familiar with that sort of language, effectively JAM provides 341 secure, quote-unquote, Turing complete. It's as Turing complete as everything in blockchain up until now. Stateless rollups. And it has one Turing complete smart contract chain that can kind of take the results of these stateless rollups and do something with them. The stateless rollups have common access to a 1.6 petabyte DA store, synchronized with 6-second latency, but if you happen to be using the same core, with instantaneous latency. So how do we do this? This seems like it's a very I mean, yeah, to me at least, it seems like it's a very big technological advancement. How do we do it? Well, we have a few different tricks, a few different mechanisms or algorithms or designs or innovations. First one is ELVs, or what I call cynical rollups. Cynical rollups are a way of very speedily coming to a conclusion over whether a particular piece of computation, as reported, is in fact correct. It's rollups. So up until now, there have generally been two big branches of rollups. One of them is ZK rollups, and the other is what are called optimistic rollups. Optimistic rollups is an incredible misnomer. In fact, a much, much more accurate name for them would be pessimistic rollups. This particular rollup technology, optimistic rollups, assume that the work that has been proposed, or the results of the work that has been proposed, are wrong, and therefore it doesn't do anything about it for a fairly large timeout. Usually the timeout is pretty substantial. So it's anywhere from half an hour to 4 days. And it just assumes that it's wrong, that it's fraudulent. And for this timeout, it allows anyone or one of a number of validators, depending on exactly how it works, to come forward with a proof that it's fraudulent. 99.9% of the time, it's not fraudulent. But nonetheless, optimistic rollups take the very pessimistic opinion that it will be fraudulent and don't do anything. They don't act on this work. This is really crappy. But they succeeded at marketing. Instead, we have cynical rollups. Cynical rollups also presume that there is a fraudulent activity because we can't be sure that there isn't. However, we go and actively try to seek confidence that the activity is not fraudulent. Essentially, by having vaguely, possibly honest, probably honest participants recompute the workload and check the result. And when we are confident that enough participants have done this, such that at least one of them was honest, then we are confident that the work report is valid and there was no fraud, and we move forward. And generally, it takes about 8 seconds to do this. 8 seconds compared with pessimistic rollups or optimistic rollups of at least 30 minutes. Another trick that we have up our sleeve is Safrole. Safrole is a zero-knowledge proof-based block authoring system that allows us to author a block without forks every 6 seconds without knowing who the next block author is, without anyone other than the next block author knowing who the next block author is. Ensuring that the next block author is unknown until they've authored the block and started distributing it is crucial if we are to avoid a certain class of attacks. And this goes all the way back to that long-term thinking versus short-term results. If we are to build secure, resilient systems, then we cannot have it be widely known who the next block author is, because they can be DOSed. They can be taken offline. And this can form a key part of an attack that might, for example, prevent certain liquidity from being exercised, or the blockchain in general, like fraud proofs, from being provided, or whatever. The next trick that we have is Grandpa. Grandpa is near instant finality gadget that is adaptive to the network conditions. So most finality gadgets operate on a fixed period basis. They finalize either every block at the point that the block is produced, or they finalize at some multi-block period. So Ethereum, for example, finalizes every about 15 minutes. Cosmos will try to finalize just actually as the blocks are being produced with Tendermint. Now, the problem with Ethereum finalizing every 15 minutes is that, well, you don't get a finality proof for, most of the time. So on average, your finality proof is going to be about 7.5 minutes old. Yeah, like the expected age of your finality proof is going to be 7.5 minutes, which is a long time if you're doing some cross-chain transfer. Yeah, I don't want to wait 7.5 minutes to see my tokens move from one network to another. And the problem with the Cosmos thing is that, well, network conditions may degrade. And if network conditions degrade, then your block production is now tied to your finality. Finality is a much heavier network operation than block production. Block production is order n. It's basically one node has to send a block to n other nodes, whereas finality is order n squared. All nodes have to share their opinions on which is the most final block with all other nodes. If network conditions degrade, finality is the first thing to go. If you tie that to your block production, and you're not allowed to produce blocks until the last one's been finalized, then your block production becomes the first thing to go. This is an issue. Grandpa is a separate protocol, which means block production is never the first thing to go. But also, if network conditions degrade, Grandpa eventually just reduces or increases the latency. Yeah, reduces how reactive it is. And it does this in a very mathematically clever way, so that it's always operating at optimal latency for the network. Finally, and the thing that's coming really key innovation for Jam is PVM, Polkadot Virtual Machine. This is a new recompiling virtual machine instruction set architecture based on RISC-V. It's very fast. So let's talk a little bit about the PVM. PVM is one of the key innovations for Jam, and it allows Jam to do some of its magic. So as I say, it's an instruction set architecture based upon RISC-V. RISC-V, if you're not familiar with it, is a instruction set architecture which was devised, I think, I might be wrong here, if memory serves correctly, in Stanford under a particular academic there. I think this is the 5th iteration. I think it started with like RISC-1, and we're now at RISC-V. RISC-V has found quite a lot of success. You can actually buy hardware processors that execute RISC-V code natively. We don't require this in Jam. There's really no need for it, but in principle they are there to buy. There's a market for them. Now, RISC-V code can easily be sort of recompiled or translated into PVM code. They're quite similar, right? There are a few important differences, which is why it's a new name, but they are quite similar. They're similar enough that it's really a very small, short executable that just translates the code. PVM has 13 64-bit registers, and it has a memory model that is very familiar if you were used to working on regular computers. Right? It's 32-bit address space, 4 kilobyte pages. A page can be mapped or not mapped. It's very easy. It differs slightly from regular silicon in that it has a Harvard architecture. So the code is stored separately to all the addressable data. Right? Code is not directly addressable. Just sort of it sits in its sort of off to the side in its own little storage. Now, crucially, PVM code, it turns out, due to the design that we have, can be recompiled in linear time, actually recompiled very, very quickly in linear time, into x64 code that runs on machines like this. This is code that can, it turns out, be dynamically metered, just like in the EVM with gas, dynamically metered with minimal overhead, maybe about 10%. PVM, because it stores the stack inside of main memory, unlike WebAssembly, which stores the stack outside in some opaque data structure, lends itself well to implementing continuations. And our internal implementation of Polkadot Virtual Machine, which is a standard specification, it achieves about 45% of native x64 speed. Native x64 speed. The speed that this modern laptop that I bought 3 days ago, can run software itself on silicon. 45% of that. This means it's multiple orders of magnitude faster than anything else in blockchain, apart from maybe Polkadot with WebAssembly. But this has a few extra advantages to Polkadot with WebAssembly, which is this ability to be recompiled linear time, the ability to be metered with minimal overhead, and the ability to host continuations. And just to be clear, this 45% figure, this is the difference in time that it would take for any given program when comparing the natively compiled version of that program to a version of that program compiled into PVM and then recompiled back into x64. That's how much that sort of little detour costs. And that includes the recompilation cost, right? The time to recompile it into x64 code. All right, so let's talk a bit more deeply about Jam's service architecture. So shared state inside of Jam, inside of a Jam instance, is arranged into services, just like shared state in Ethereum is arranged into smart contracts, right? Very simple. So we kind of call smart contracts services, basically. Services have a single piece of code with 3 entry points: refine, accumulate, and on-transfer. So 3 pieces of code for every smart contract or service. Refine is the code that operates in the middle bit on those thick arrows. Accumulate is the code that operates on the right bit, those thin arrows. On-transfer also operates on the right bit. It just handles messages from other services. Services are a bit like smart contracts, as I said, except they have a few differences. Their computation is staged, so we already know that these state refine and accumulate, and kind of on-transfer. So there are 3 different stages of computation. Not only is the computation staged, it's pipelined. Refine comes before accumulate, but while accumulate of an earlier service, of an earlier piece of work is happening, an earlier transaction, if you like, refine of a newer transaction can be executed. Beyond that, it's distributed. Multiple refines, even of the same service, can be executing at once. In addition to that, there is bulk purchase of gas or block space or core time, whatever you want to call it. The thing that Jam is selling, you purchase in bulk. You purchase it, Jam sells it, or Polkadot will sell it, I suppose, on a month-by-month basis. You buy a whole core for a month. You can partition it up and split it up and do all sorts of stuff with it and sell it off in smaller pieces, of course. But that's the basis for Jam's resource provision, right? It's much bulk. Why is it much more bulk? Well, because it doesn't make sense to sell off on a per transaction thing because the transactions are so small. Jam will get bogged down in processing transactions and not in actually doing computation. So it makes a lot more sense at this sort of L1 or L0 level to only sell big chunks, right? We're like the whole dealer. Wholesaler. Also, Jam is generally asynchronous. Services kind of don't operate synchronously. I'm going to go into this in a second. Jam is permissionless, right? Or at least it's designed so it can be permissionless. It's designed to work in a permissionless environment. An example service could be, for example, for the parachain service, a service that does what Polkadot 1 does currently. That would be one big service, but just one. Services are very powerful things. Introducing a new service is permissionless. Anyone can do it as long as they put up the tokens. Jam is agnostic to the higher level aspects of blockchain, staking, economics, governance. Jam is agnostic to this. This doesn't form part of the Jam protocol. Jam provides a machine. That's the M of Jam. Join, accumulate, machine. Jam is a decentralized computer. It doesn't care about this stuff. If we look at the Jam pipeline, what's really happening when Jam does work? Well, the work comes in at the top. And first, before we do any of the work, we check to make sure we should be doing the work, right? In Ethereum, this will be done by checking to make sure that the transacting account is able to pay the gas. In Jam, we don't have this just-in-time gas purchasing. Instead, we have a much more general thing called the authorization system. And first we do this. We run the authorization system. We authorize the work to be done. If we're convinced that the work is authorized, then we move on to the next step, refine. This is the very heavy duty processing, right? The thick arrow in the middle, the one that has access to the data lake and has huge amounts of computation. Both of these happen in core, in the middle part of that diagram I showed you. The authorize is authorizer code. This is separate to the service code. The refine is the service code, the code of the service that we are actually wanting to do work with. The smart contract code, if you like. When we finish doing the refine, we send it on into the accumulate stage and any transfers. This is still in the service code, but instead of operating in core on the thick arrows, it's operating quote unquote on chain with the thin arrows. This is where all of the different work that refine has done comes together and synchronizes, becomes coherent again. So for this particular piece of work, in those top two parts, the system was incoherent. In principle, colliding or mutually incompatible workloads may have been being done, but accumulate makes it all okay. Accumulate is where we basically, if two workloads are mutually incompatible, we throw away one of them in accumulate. We somehow make the system come into some coherent whole. To explain this a little bit further, I'm going to give you some little emojis. So we call a piece of work a transaction, basically, but it doesn't have a signature. So we're going to call it an item. So it's a work item, a piece of work that we want doing. It's associated with a service, and we give it this little notebook thing. Now we can take a few items, as well as an authorization token, some sort of proof. We give to some authorizer code that this work is work that we want to be done. And we form a package with that, a box, right? That's the work package. Work packages tend to be quite big, maybe around 12 megabytes. Now we also have this concept of a digest. The digest is a small piece of data, also associated with a service, and it's the output of refine. So after we've done the refine stage, this hardcore computation, we get out a small little piece of data, in comparison, called a digest. So, how do our different stages work? Well, authorize takes a work package, and it gives us some, what we call a trace, or a little label that tells us why it was authorized. And it's any data that the authorizer thinks is pertinent for the other parts of the pipeline. Now, let's recall that a work package is actually just a token, an authentication token, an authorization token, with some work items, some transactions, if you like. Refine then takes one of these transactions, let's say a transaction for the red service, combines it with the this little trace, this piece of data from the authorizer, and it gives us a digest. And the digest is associated with that same service, the red service. We then join all of the red digests, all the digests that are newly computed that are concerning the red service, along with all of their traces. And we kind of join them together and then accumulate them. So accumulation happens on maybe multiple digests, but always from the same service. And it turns out accumulate gives us some sort of hash result, which makes its way eventually on chain. So authorize can inspect the entire package. The package includes this authorization token. So it can use this token to work out if the package is valid, is good for being, basically good for work. If the authorizer thinks the package isn't good for work, it panics. And that's the end of the pipeline. We haven't done much work by this point. Otherwise, it provides some trace. We have a way of determining whether a given piece of work is allowed to be done on a core. Every core has what's called an authorizer pool and an authorizer queue. Queue isn't so important. It just replenishes the pool. The pool is important. The pool is full of commitments, cryptographic commitments to particular authorizers. And for a work package to be valid, an authorizer in the pool of the core it's going to be authorized on, it's going to be computed on, must not panic when fed the work package. It must exit in success and give us a trace. Assuming it does, we move into the refine. Now, refine is performed on a single work item. It may inspect the output, that trace from the authorize stage. And it may also inspect any other items in a work package. This is crucial. This allows us to co-schedule two different pieces of work at the same time in the same core, essentially allowing for synchronous composition without much of a cost. So the ability for every work item to look at every other work item and all of its data is a very important property. It can also look at data that's already been placed on chain and invoke other PVM instances. It can create new virtual machines and set them off. It can create new virtual machines and put whatever it wants into their memory and set them off, wait until they stop or have completed some amount of computation, some number of steps, and then read their memory, right? This is very, very important. I'll show you why in a second. Now, items can be quite big, as I mentioned, up to 12 megabytes of data that can be read from the data lake or fed in as totally external data. They can also place 12 megabytes of data into the data lake. And they can execute for about 5 seconds of PVM gas. 5 seconds of PVM gas equates to about 2 to 2.5 seconds of native x64 time. And this happens every 6 seconds, right? Every jam core runs somewhere around a third or so of a native AMD Threadripper 5 gigahertz CPU core. That's a pretty hefty amount of computation. And they yield up to 48 kilobytes of digest. This is the information that feeds its way into accumulate. As I said, accumulate can be performed on one or more digests of a service at a time. It can inspect all the traces, see why it was authorized, and for every refine output, every digest coming in, it can execute for up to 10 milliseconds of PVM gas. That doesn't sound so much compared to the 5 seconds over here, but we have to remember, accumulate happens on chain. It's fully coherent, fully synchronous. This is why it's not so much. But you can actually do quite a lot in 10 milliseconds. You can maybe do, 10,000 database operations, right? We reckon that we can do about 1 million database operations a second. It can transfer funds, alter state, do all the usual stuff that you'd expect to be able to do in a multi-actor environment. It can create new services, upgrade code. In fact, it's the only way to create services. On Ethereum, you can make a transaction that creates a new smart contract, right? You can just literally, in a totally empty Ethereum system, make a transaction that will create a smart contract. It's built in. It's not built into Jam. Jam is much purer as a machine. If you want to be able to create a service in Jam, there needs to already be a service that provides that service for you. Yeah? If there isn't, you can't create a service. Now, this provides some very interesting possibilities for restricting what any particular Jam instance might do. But what it basically means is that for the most part, your Genesis block has to have at least one service in that provides for creating a service. As I said, Jam services are generally asynchronous. Now, how does this work when we're actually executing code in a coherent environment? Well, basically, transfers are processed after all of your accumulation is finished, and indeed everything else's accumulation is finished. Whereas foreign state reads are only interpreted as before any execution has started, right? So when you read another service's state, it's as though that service hasn't done anything since the beginning of your execution. And when you transfer a message into another service, that service won't see it until all of the execution is finished. This allows us to be asynchronous. It also allows us a potentially future path to both parallelization within the same machine and composition of multiple Jam instances. But that's really a topic for another talk. All right. Now, I'm going to give you some examples of services that are going to run on Jam. First one is Core VM. Might better be named Jam Docker. This is essentially runs a PC on Jam, right? It runs a regular, more or less, computer inside of Jam. There's a service that lets you do that. Now, unfortunately, the demo that I want to give you isn't quite at the point that I wish it were, but I can give you some demo of this. But I want to explain this a little bit first. So I've talked a little bit about Jam and having lots of computation power and memory bandwidth and DA and so forth. But it's still a very particular environment for doing computation in, right? It's got two parts to it. It's got this DA store. It's got particular. It's quite weird, right? It's a computation and execution environment you would need to learn. I don't think it's that weird, and I think you probably can learn it quite easily. But nonetheless, it's not something that anyone is as yet going to be used to. And it certainly doesn't look like what we want. This is what we want, right? Where does Core VM come from? Well, it comes from the perspective that blockchain developer experience is rubbish. It's rubbish. I mean, it's fun sometimes, but this isn't a developer experience that is easy to sell to regular developers. You've got weird storage, right? 32 byte to 32 byte mapping that has Merkleization behind it. It's small. It's very odd. It's not something that you're going to be used to if you're used to just regular machines where basically you have files that you can store things into, or maybe a server that you can push thing and pull thing from. It's nothing like that model. It's got weird execution, right? You have these crazy limits, like block gas limits, where if it takes too long to do a particular operation, then that's it. You're done. It's broken. You can never do anything else. This is also very odd, very weird. Just the fact that you got gas is weird. It's very odd. You don't have a choice of languages generally, and if you do, it's usually a couple of very particular languages. There might be very particular idioms that you need to use in the language, and if you don't use it, it'll break. or you just can't use some functionality of the execution environment unless you use these idioms. Oftentimes it's full of pitfalls. Look at the DAO disaster of 2016. Code that looked fine, code that was audited, but ultimately was broken. And then probably one of the most weird things is that you don't have control over your execution loop. After interpreting every piece of data from the external world, you have to destroy all of your working state. This is crazy. It's like, I don't want to have to destroy my working state. What if I need to do a huge migration? This doesn't make sense. This limits developers. It limits the developer market, and it limits potential use cases. And it makes creating certain pieces of software really hard, really, really hard. This is what we want. We don't want the arrows to be broken every block. We don't have to, pack up our working state and then unpack at the beginning of every block. So, what does Core VM do? Well, Core VM is a bit like an operating system. It takes away the need to consider all of these hardware level things, all these things that are kind of like decentralized hardware, gas and block limits and storage, right? This is all removed. And instead it gives you a regular machine, a machine to which you can compile pretty much any code. This is Core VM. This is how we draw it. Now the lines are still there. The vertical lines are still there, indicating that each Core VM process runs essentially in its own sandbox, right? But they can talk to each other. That's the dotted lines, right? So they can send messages to each other. There's that sort of inter-process messaging. But you'll notice two things that differentiate this from other pictures that I've drawn for you. The first thing is that the arrows go all the way from the top to the bottom, indicating continuous execution, no breaks for the blocks. All right? The second thing that you'll notice is the arrows have an orange background, not a blue background, indicating totally regular memory access. Yeah. They're also thick, indicating it can do a lot of computation. So you might think of Core VM as Docker for Jam. It provides a regular execution environment for normal software. It emulates a machine. That machine has near native x64 speed. It's RISC-V compatible, which means you can target regular software onto the machine. Has paged memory, like normal machines. Has continuous execution, like normal machines. It provides message passing between processes, like normal machines. This is a machine that can run normal software compiled from normal languages using normal abstractions. It can run any software, even software that's not meant for blockchain. Software like Doom. So I'm going to switch to a Intel machine now. And hopefully this will appear. There we go. So what this does, I'm going to run a script. What the script does is it sets up a small test network, a network of 6 nodes. They are all validator nodes. We have normally we have 3 validator nodes operating 1 core. So with 6 validator nodes, we have 2 cores. So it's a very small Jam instance. Normally we would have 1,023 validator nodes operating 341 cores. But this is only a little laptop. So they all have to share the same CPU. And it has 2 other processes going on. One of them is a sort of builder process. that helps Core VM understand which memory pages are needed to be fetched from the DA each 6 seconds. And the other process is one that is monitoring the DA for video frames. Why would it monitor the DA for video frames? Well, Doom wants a graphics card to write its graphics to, right? It's a game. It doesn't make much sense if you play a game without any way of seeing what the game is doing. And of course, a blockchain doesn't really have a video card. So what we do in Core VM is we create a virtual video card, a decentralized video card. And actually, we just export all of the video frames out into the data lake. Our bandwidth is good enough that we can actually export video frames at 30 FPS into the data lake, in addition to fetching any memory that Doom might require to run. Like any RAM of that PC that is running Doom. So you see it's spinning up. And it will take a little while because it's essentially setting things up so that it will understand which, so it has to deploy the service, wait until it's finalized, put the code in and so forth. So it takes a couple of blocks to do that. And then it will, what are we doing? Ah, yes, I did make a code change. Let's just revert the code, git stash, should do the trick. And the Core VM service, let's think about this. What is it doing? So it wants to provide a regular virtual machine. So to provide a regular virtual machine and do so with block gas limits, it's going to need to be able to unpack the previous bunch of memory. So we need to be able to unpack the memory, create the virtual machine that was previously running, keep it running, allow it to run for a while, and then pack it up again and put it in the DA, put it back into the storage. Now, I'm not sure it's going to put the video frame. Yeah. Right. Okay. I'm gonna continue explaining this. I will need 2 minutes of coding time to actually make this work again. But for now, we'll just continue. So we need to take the previous state of the machine out of the DA, feed it into the memory of our internal instance, run it to generate 6 seconds worth of frames, pack up any of the changed RAM pages and put it back into the DA for next time, and then also take any of the video frames and put those into the DA as well. We will then have our display process, which will check to see any new video frames that have arrived, look at their timestamp, and display them according to their frame index. And it will obviously have to take those frames out of the DA. So you see 2 arrows going to the display process. One of the arrows is looking for the cryptographic references to those frames. The other arrow is actually pulling the data. The service itself can't store the frames actually on the chain because that would be way too much data. So it has to take them out of the DA. The sequencer, as I mentioned, is really just sort of bumping Core VM along and letting it know which memory pages it's going to need for the next 6 seconds. To do that, it has its own Doom, it has its own PVM instance and therefore Doom instance running, and it's sort of checking which pages the instance is hitting and building up a table of them so that it can then ping it with the correct data. And that's how we run regular software on chain. So this is only possible because we have this high bandwidth, properly integrated data availability system, the distributed decentralized data lake. It also helps that we are pipelining everything. We're pipelining blocks more than we normally would. We're using refine at the same time as accumulate. And this is really crucial in getting this level of performance. And of course, the PVM allows us to do this by virtue of it being able to support continuations. So moving beyond core VM, what's the purpose of sort of core VM? I mean, core VM on its own seems like a bit of a waste of time, like no one's going to play Doom on a blockchain. But it allows us to form a stepping stone into the next stage of blockchain computation. And to understand why we need, or why we're going in this direction, we have to return to that thing I was talking about earlier, persistent state partitioning. What does more chains solve? Well, it solves having more computation. This is what we want. We want to scale out. But the big problem with it is, of course, fragmentation. As we scale out, the network effects reduce. As we fragment our ecosystem, not to mention industry, the network effects, these things that can really provide very interesting compositional use cases, reduce. It limits the use cases that we can create. It limits the possibility of atomicity. It limits developability. It's hard to develop software that sits across asynchronous, loosely composable systems. And for teams that are trying to deploy, it forces them to make a decision to commit into a particular L2 or particular sub-ecosystem without having particularly great information on what that sub-ecosystem, what that L2 is going to look like in a year's time, in 2 years' time. This is what we wanted. Jam isn't that, but Jam can give us core play. So core play uses Jam to create this kind of a computation environment. We have arrows, they're orange. If you remember, orange arrows is what we wanted. We don't want crazy memory stuff, right? We want just continuous execution. The arrows go top to bottom, continuous execution. Indeed, core play is starting to look a lot like the thing that we were chasing. Now, there are still partitions. We can't avoid there being partitions. There have to be partitions, or we'll end up breaking the laws of physics, well, trying to. We have to partition our state. But we can be cleverer about how we partition our state. We don't have to partition it in a static way, in a persistent way, in a permanent way. We don't have to partition it over the lines of the borders and boundaries of L2s, right? Of different ecosystems, of different tokens and different centralization factors and different logos and different leaders and so forth. No. We can partition it in the most economically sensible way, and we can keep repartitioning it often. And this is what core play is designed to facilitate as efficiently and optimally as possible. You can think of it as a smart contract operating system for Jam, and it sits as both a service and an L2. It requires an L2. That's somewhat unfortunate, but it is simply the reality. What does it provide? Essentially, actor-based smart contracts. They're not really smart contracts in the sense of Ethereum smart contracts because they're not transactive, right? I mean, they don't need to be. It's not the case that they just take a transaction, execute for a little bit of time, and then stop, and everything gets packed up, or their working memory gets thrown out. No. These are normal software processes. They could be Doom, but probably they won't be Doom. But they might be sophisticated. They might make a lot of use of the DA, and probably they're going to look quite a lot like actors. If you want to take your Solidity code and compile it into this, of course you'll be able to. This is a much more powerful programming model than the EVM execution architecture. Now, interestingly, because we're doing our partitioning at the time of execution rather than at some fixed, set of borders and boundaries according to the L2 landscape. When we add more actors, we can just partition them across more cores. We can scale out core play into more cores. Can't really scale out a single actor into more cores. Actors are designed to be synchronous machines. But we can have more cores with which to partition our sort of actor community across. And this allows us to scale out without breaking any of our previous guarantees. We still get global atomicity. We get atomicity between any set of actors simply by co-scheduling those actors on the same core. And they can talk to each other synchronously. Very much like in the Ethereum world, co-scheduling blockchains. But we get zero fragmentation. Why? Well, because we can repartition as often as we want. How? Well, the same reasons that we were able to do core VM, combined with the fact that we have small state atoms. Actors have much less state than blockchains. Combined with the fact that we regularly repartition and therefore allow for synchronous composability with actors that at the time need to be synchronously composed. Essentially giving economic efficient co-scheduling, bringing together actors whose economies consider co-scheduling valuable and are willing to pay for it. So why don't we just use co-sequencing of blockchains? Well, basically, it's a very similar proposition, but blockchains are huge. They're massive. And co-sequencing huge state transition systems results in massive inefficiencies and massive centralization bias. We end up with one huge co-sequencer that is basically the single authority on what gets through into any chain that happens to be being co-sequenced. This is an issue. This isn't Web3. This isn't resilient. Why is it like this? Well, even just tracking the opportunity, like the economic value of co-sequencing across blockchains is hard. You have to be running full nodes and doing quite a lot of analysis on those chains. You have to then track the entanglement, right? Co-sequencing is a form of causal entanglement. Essentially, one blockchain, transaction on one blockchain, or the effects of a transaction on one blockchain, must not be felt until the effects of another transaction on another blockchain are known and certain to be finalized. Only then can the effects on that other blockchain be felt. Now, this problem grows as you try to co-sequence more blockchains. Yeah? Because you have to track that causal entanglement, not just for one other blockchain, but for all of the other causally entangled blockchains. Now, this becomes a bit of an issue because it grows order n squared. Every blockchain that is part of the entanglement has to track every other blockchain and not do anything, not affect any transaction consequence until it's certain that it's finalized across all of those other blockchains. Even just tracking the entanglement is hard. This is only really viable even on relatively few blockchains using a very powerful node. And it becomes increasingly harder, and therefore you need an increasingly powerful node that's backed by increasing amounts of stake, that feeds its co-sequence blocks to increasing amounts of validators before, if you want to do more than a few blockchains. Certainly, if we tried to roll this out to something the size of Jam with 341 co-sequenced blockchains, it would be mad. What about intent solvers? They're not a general solution. Intent solvers take a fragmented world and they try to create a recipe for utilizing it for any particular thing that a user wants to do. They don't allow the individual trustless components that sit in these fragments to actually interact directly. They generally also don't tend to be a very general solution. They only work on the tasks that are supported by the intent solver network. What about multiple instances of something? That also doesn't really work. You're going to split your capital pool. You're going to split your resources between those different instances. Even if you employ rebalancers, that resource will only exist on one at a time, one instance at a time. Why don't we use ZK for scaling? This is a question that I do get asked sometimes. Well, basically because cynical rollups provide substantially better price or cost than ZK rollups currently. ZK is an interesting technology, and it's already useful for a number of things, but scaling computational correctness isn't one of them. The people that I talk to about ZK don't even think that it will outperform cryptoeconomic solutions in the long term. The suspicion with ZK is that it will probably get to about maybe 50,000 times the cost of a cryptoeconomic solution and then kind of stop. That further improvements will be of minimal reduction in time and cost. We'll see how that plays out. But certainly for now, ZK scaling solutions are not cost efficient. To give you an example of the numbers, it takes PVM, if we say that it takes PVM, we call this the basic amount of time to do some computation and check that it's correct. It takes the Jam network about 30 PVM executions. So it's like 30 times as much time to check correctness as a whole over the network as just running the thing itself. It takes a ZK generator, a zero knowledge proof generator, about 60 million times the cost for generating the proof compared to the cost for just executing the computation under PVM. Now, for this, we're using risk zero because we want to do general purpose computation. If you limit the computation that you want to do to very particular domain specific and well ZK optimized form, then you'll probably get a much lower multiplier. But if you want to have like a very general network, the sort of network that can run Doom, then you're going to be stuck with this substantial multiplier. And this multiplier will probably go down. We already see researchers doing some very interesting work with ZK. But it will take a while for it to get down from being 2 million times more expensive to being, approximately the same cost. This isn't going to happen overnight. It'll probably take some years. Good. I will... I'll provide a quick demo of the... I'll provide a quick demo of the Jam environment first. And then if there's time, I'll get on to trying to fix the Doom thing. I know what's wrong with it, but it'll take me a minute or two to do it. So this is a Jam REPL. It's like a sort of debug console for Jam. And in this, we can move the chain forward, author new blocks whenever we want. We can introduce new work packages, work items, and sort of play around with services that have been deployed on Jam. So what I want to show you first is the demo service. This is a service that I made for demoing Jam. Here is the code for the demo service. I hope you can read it. Yeah, I think it's readable. So as I mentioned before, it's got this refine and accumulate model. The refine code, it doesn't do very much, right? It's really just about showing you the data pathways. So it's going to take the output from the authorization agent, print a debug message, create a little message that shows us what the payload is and the authentication output is, and then basically put the info message into the DA store and show us, or pass into accumulate the data that we're working with, the payload, the authentication output, and this identity in the DA store. If we go into the accumulate, it's going to take this information, these three fields, decode them, and then stick them into storage. So we're going to expect that these storage items will be written to. So let's have a look at this. Now, at the moment, there is no demo service on this chain. As I mentioned, you have to create you have to start the chain with a service before you can even do anything with the chain. If you don't have any services on the chain, on Jam, then you will just never be able to do anything with it. So let's have a look at what services we have. You can list the services with ls, and it tells us we have service 0. This is the Genesis block. There's already a service sort of in the Genesis block. And this is the Bootstrap service. Bootstrap service is a service. It's a bit like on a PC. When you turn it on, it doesn't instantly go into Windows or Mac OS or whatever. There will be a little bit of software first that it runs, like the Bootstrap software, yeah, the BIOS, yeah, basic I/O service. And this is there to initialize certain things like the hard disk, and then read the code for the operating system off the disk and then start executing it. Well, it's kind of the same with Jam, right? Jam is actually, you'll find out, quite a lot like a regular computer. It's architected like a regular computer in many ways. And one of the ways that you kind of know that you'll find is that it needs this Bootstrap service. The Bootstrap service essentially allows us to load software into Jam, right? And the way that we do this, we have to give it a work package with a work item inside. And that work package uses the sort of instruction format of the Bootstrap service. As it happens, this debug console understands this instruction format and that provides a command called boot create service, which allows us to load software on. We can then tell it what software we want, and we're going to use demo service.pvm. This is a pre-compiled, I previously compiled this file into this PVM code. We can also give it some initial balance, which I will do because we're going to write some stuff into its storage, and to do the writing into storage, it needs to be given balance. All right, there we are. So it's told us it's created this service, and we've seen there's a few debug messages here that tell us what's going on behind the scenes. It's going through an authorization code inside of PVM. It's then going into the Bootstrap service refine, and then again into the Bootstrap service accumulate. So it's working its way through authorizer, refine, and accumulate, just as I mentioned in the slides. And then we get this like extra debug message at the bottom telling it's created a service, and this is the ID of the service. So far, so good. It looks very promising. So if we list the services, we see, yes, there's the old service 0, the Bootstrap service, that's still there. But also now we have this new service, E1A04AD8, which is the same as this, but we're calling it A because it's a lot easier to type A than it is to type that hex. And it has some balance. It has the million that we gave it and some extra that it took because it needs it to store its code. Okay, very good so far. So let's just check its storage. We can read storage with the read storage command, and we can read the storage of of A. It will default to A. We can read the storage key. Let's say last payload, I think it was. And we could say A here, but it will default to A, so I'm not going to put it in, and it's empty. Of course it's empty because we haven't given it any work to do yet. So let's give it some work to do. We're going to give work item. And we want to tell A, we're going to give A a work item. Let's say a work item, hello, Hangzhou. Hello, Hangzhou. Okay. Aha. One pending work item. So we can build work packages one work item at a time. In order to like put all the work items, or one work item into a package and then send it to the chain, we use the guarantee command. So what this is going to do is send hello Hangzhou into the demo service back here and into the refiner, the demo service. So we expect to see some debug outputs, and we expect that when it gets through to accumulate, it's going to set the storage of last payload. Okay, let's see if that works. And it looks like it might have worked. Let's read the storage again, and bam, there it is. So this is like your basic transaction, if you like. Now it's not doing anything like checking signatures, because it doesn't. That's not what Jam does, like by default. To make it check signatures, you'd put some sort of signature checking code, some signature checking logic into the authorizer or into the service code. For now, we're just doing something simple like this. But in principle, it supports all of this, right? This is just higher level stuff for Jam, because Jam is virtual silicon. It's decentralized silicon. It's designed to be a very general computer, not to be a smart contract platform. Put the smart contract platform on top. Okay, let's just do one other quick thing. Yes. So if you remember, it also placed a message into DA. So let's have a look to see if we can find what that message is. The DA message, I think, is in last info ID. It might be last ID, I can't remember. No, last info ID. And there we are. So it's telling us it's a DA index 0 for this block, for this core. Let's have a look in our DA and see if we can find it. So LST gives us the segment tree in DA. And at the moment, there's only one segment tree in DA, only one block that has actually exported, or indeed one work package that has exported any data into the DA. It's surprisingly enough the one that we actually did ourselves. And it happened at block time 4 in core 0. This work package, which was, if you look, and it's the same as that work package, same ID. So that's good. It's the one that we're thinking of. It's got a particular root. We don't care about the root. Item 0, the same as this, has a value of payload, hello Hangzhou, auth output this. That's the message that we created in our own logic, right? That's this message here. We created it in our own logic and actually pushed it out into the DA. And it's as simple as that. Just export slice, right? That's all. That's as much as you need to do. It's going to sit in the DA. If you want to import it, it's very easy. You just use import slice. And you have to give it the 0 that we know about and this, either of these two things. Right? You only need one of them. And these are the cryptographic commitments. Good. One other quick thing that I'll show is sending it a message. So it turns out that our Bootstrap service has a transfer command. We can transfer a message to any service we want. Transfer a message and some funds. I don't need to send any funds, but we will send a message. Actually, I can't remember whether it's funds first or message first. So let's just help. It's funds first. Okay, no funds, and we're going to say I don't know, money for nothing. Money for nothing. So we're sending it a message. We're using the Bootstrap service to initiate the message send. It's going to arrive at our demo service. What is it going to do? Let's have a look at the code. And on transfer, so this is when we receive a message, we get given, here are all the items. We're going to do a debug message just to see what it's about, make a message with this format command, this format thing, and then set a storage item, last TX. So before we do this, let's just check that last TX is empty, that there's no funny business going on. And we can do that with read storage last TX. And indeed it is empty. So let's do boot transfer, no funds, money for nothing. I hope you're impressed with my one-handed typing. And there we go. So going through the authorizer again, Bootstrap service, all right, blah, blah, blah. It's got into accumulate. It's attempting a transfer. It's good. Okay. and done the transfer, and it looks like it's good. So let's have a look again at that storage item, and sure enough, there's the message telling us it knows it's been given something from service 0, and it knows what the memo is. So this is just showing you this is a coherent, smart contract-ish environment that Jam is giving, and I kind of want to get across the idea that this is just a pretty regular computer. This is a lot more regular of an interaction, I hope you'll see, than what you would do on a sort of Ethereum blockchain, right? The interaction feels more like you're just at a console giving the computer commands. Okay, I'm going to give this one more go. So let's unlock this and see if I can. I think all we need to do is alter the right now. Alter the. Let's have a look. Crates, Doom Builder, Cargo Tommel, and change the. You want to do something? Oh yeah, cheers. And then if this is a funny thing. It turns out that SDL, which we use to describe the video, to put the video on the screen, just totally fails if we use the bundled version of it. So we have to use the system version of it. But hopefully, when it gets to actually putting a video window on screen, it will actually work now. But we'll see. Aha! Yes. There it is. Let's see if I can make this big. Yeah. So this is, as I mentioned, coming off the blockchain. So the blockchain is outputting these frames 6 seconds at a time into the DA store. And then we have a viewer process which has opened an SDL window using SDL and is reading out of the DA store according to the frames, according to the references that were placed on chain by CoreVM. It's just displaying those graphics. The graphics, for what it's worth, are 320 by 200 pixels with an 8-bit palette. So every frame takes about 16 kilobytes. I think that's right. And then if we have 30 frames a second, that's 180 frames every 6 seconds. If you multiply that 180 by 16K, you don't, and it's not so big. It's like under the 12 megabytes that we have. It's like well under the 12 megabytes that we have for our DA read writing. Now, in addition to that, we have to keep the memory, the RAM of our machine that is running Doom, right? Doom has no idea it's running on a blockchain. Yeah, that would defeat the purpose. As far as Doom's concerned, this is just a regular sort of PC. I mean, it's a PC with a PVM execution, a PVM instruction architecture, but still a PC. Like we can compile Doom to PVM, but it expects a continuous environment. Doom doesn't understand about block gas limits or anything like this. So we have to provide it with a continuous environment. We have to provide it with 32-bit page memory addressing. So we simulate this for Doom by creating a PVM instance, and then at the beginning of every work package, every block if you like, we unpack the previous block's memory of this machine into the new machine. We then kick it off with the Doom executable, which just basically, because the stack's there as part of memory, it just continues working as though nothing has happened. And then at the end of the execution time, after 5 seconds or whatever of PVM time, we then take all of the pages that have changed, record how they've changed, get cryptographic commitments, and store those commitments sort of in the main service executable in accumulate, the main service state in accumulate, and then store the actual 4 kilobyte memory pages back in the DA. And then in addition to all of this, of course, we're throwing the video frames into the DA and storing references to those in the main service state. So this is how you create a sort of continuous execution CPU on chain, as well as a decentralized video card. Right? And in principle, you could have a decentralized console as well, right? You could just stick all of the messages going into the debug log or into the std out, std out, also into the DA. And you could, if you want to do input, you could, inside of the input, the extrinsic data of the work items, which at the moment is basically empty, there's nothing going in, you could put user input, keyboard input, yeah? And then basically feed that into Doom as a virtual keyboard driver. Yeah. And this is probably something that we'll extend Core VM to do, mostly for fun. But yeah, so Core VM is the clever bit, right? And actually Jam is the really clever bit. But Core VM is this service that sits on Jam and provides this container, right? This PVM execution container. And inside of this container, you can put basically any software, as long as it compiles to bare metal, or as long as you can put whatever drivers it needs. You can make decentralized counterparts, then it'll run any software. Good. All right. I hope you enjoyed it. That's it for now. Thank you for your attention.